Welcome to a deep dive into the fascinating world of chemistry. We're tackling the periodic table today,
A real foundational topic for sure.
and we really want to get into how it helps us understand elements, not just memorize them.
Like how this table makes sense of the elements and their properties.
Yeah, exactly.
It really is like a map to navigate the vast landscape of chemistry, wouldn't you say?
Totally. Imagine a library with all the books just thrown in randomly, right?
Yeah.
Chaos.
Yeah.
The periodic table is like the Dewey Decimal System, but for chemistry.
Right. It brings order and it reveals all those relationships between elements.
Hidden relationships.
It's amazing because this organization emerged when chemists were just drowning in element discoveries.
Oh, yeah. I mean, they had this huge puzzle with just more and more and more pieces coming all the time.
Absolutely.
Must have been overwhelming.
It was. And so early chemists tried a bunch of different approaches to make sense of it all, like Dobereiner's triad.
Yeah, Dobereiner, yeah.
He grouped elements in sets of three based on similarities, and he noticed this relationship with atomic weights.
Yeah, so he was seeing order, but just like tiny glimpses of it.
Yeah, it was a step, but a small one.
Limited in scope.
Exactly.
Yeah.
Then there was de Champ-Courtois.
Courtois.
He arranged the elements kind of visually on a cylinder, based on their properties.
Oh, wow.
And Newlands,
Yeah.
he noticed these repeating patterns every eighth element
Oh, interesting.
when they were arranged by atomic weight.
Okay, so by weight.
He actually called it the law of octaves, like music.
Oh, like a musical scale. Okay, yeah.
Yeah.
So they were getting closer, but it sounds like a lot of just, trial and error.
Oh, it was.
Yeah. So what was the turning point?
The big breakthrough, it was Dmitry Mendeleev,
Mendeleev.
often called the father of the modern periodic table. He arranged the elements by weight.
Okay.
And he saw these amazing repeating patterns.
In their properties.
Yeah, and what was revolutionary was he left gaps for undiscovered elements.
Oh, wow.
He even predicted their properties.
He was like a chemistry fortune teller.
He was. Like, take the element gallium.
Gallium.
He called it Ica aluminum.
Ica aluminum.
And predicted its density, its melting point,
Oh, wow.
even its chemical formula. And he was incredibly accurate.
I'm kidding.
Years later, when gallium was discovered, its properties matched his predictions almost perfectly.
Talk about validation.
It was huge validation.
That is amazing. What a legacy. But the periodic table we use today isn't exactly Mendeleev's, right?
You're right. In the early 20th century, there was another revolution, subatomic particle.
Oh, right.
Protons.
Yeah.
This led to a realization.
What's that?
Atomic number.
Okay.
The number of protons in an atom, that was the key, not just atomic weight.
So the periodic table, got a major upgrade.
It did. Henry Moseley,
Mowgli.
brilliant physicist he was, used X-ray spectroscopy to study elements, and he found it.
What did he find?
Direct relationship between the frequency of X-rays emitted by an element
Okay.
and its atomic number. This led to the modern periodic law.
Modern periodic law. All right.
The physical and chemical properties of the elements are periodic functions of their atomic numbers.
So it's much more than just a tool for organization.
Right.
It reflects the fundamental structure of atoms.
Yeah. It's mind-blowing, isn't it?
Totally.
It's a direct reflection of quantum mechanics,
Whoa.
which governs electrons,
Okay.
the tiny particles that determine how atoms interact.
Okay, so let's break down how this is structured. We've got rows, right?
Yeah.
Called periods, and columns called groups.
Yeah, exactly. The rows, or periods, correspond to the principal quantum numbers. Each row represents a higher energy level.
So as we move down the table,
Yeah,
we're going to higher and higher energy levels in the atoms.
that's right.
Okay. Pretty cool.
Yeah. And the columns, the groups,
Yeah, the groups, what about them?
they bring together elements with similar arrangements of their outermost electrons.
Outermost electron?
Yeah, they're valence electrons.
Valence electrons.
And this is why elements in the same group tend to have similar chemical behavior.
Okay, I see.
Think of it like this. Those outermost electrons, they're interacting with the world,
Okay.
forming bonds, driving chemical reactions.
Right, so it's like families,
Yeah,
elements in the same group share traits.
precisely. Like the alkali metals.
Alkali metals, okay.
Group 1, they're known for being extremely reactive.
Reactive, oh yeah.
Yeah, they have that one lone valence electron. Just want to give it up.
Right, and then you have, on the opposite side, the noble gases.
Yes, group 18, totally unreactive.
Totally chill,
No,
because their outer shells are totally full.
right, they've achieved electron nirvana.
They have. Okay, but we can go even deeper.
Yeah.
We can look at the
It's
blocks.
the S, P, D, and F blocks, yeah.
These blocks, they tell us what type of orbital's being filled
Exactly.
as we move across the table. Okay, orbitals.
Orbitals.
Admittedly, they're a little fuzzy for me. What do they actually tell us about the elements?
Well, think of orbitals as homes for electrons. Okay.
Homes for electrons.
The S block, for example, it has the alkali metals
Oh, okay.
and alkaline earth metals.
Yeah.
Those reactive metals we just talked about.
Right. Okay.
They tend to have low ionization energy.
Low ionization energies. Okay.
Meaning they lose those outermost electrons easily
They do.
to form positive ions.
Right. Okay.
So they're the electron donors of the table.
They are.
And then you have the P block,
The people.
a more diverse group. You've got metals, non-metals, and metalloids.
The metalloids, I remember those.
Oh, good.
The properties of both, right?
Yes, the chameleons of the table. And the P block also has some essential elements for life.
Oh, yeah, like
Carbon,
okay,
oxygen,
Right.
nitrogen.
nitrogen, yeah.
Yeah.
Makes sense.
Yeah.
Speaking of life, I'm curious about the other blocks, the D block and the F block.
Yes. A little mysterious, aren't they?
They are.
The D block houses the transition metals.
Transition metals.
You often have those beautiful colors,
Yeah.
variable oxidation states,
Oh, right.
meaning they can lose different numbers of electrons
Okay.
to form all sorts of compounds.
Right.
And they're often important catalysts,
Oh, wow.
speeding up chemical reactions.
Okay, so they're versatile in their bonding behavior.
Very much so. And finally, the F block.
The F block.
The two rows that are often separated from the main table.
Right.
They're the inner transition metals, the lanthanides and actinides.
The lanthanides and actinides.
More elusive
Right.
and often radioactive.
Oh, like uranium.
Yeah, used in nuclear power plants.
Exactly.
Yeah. The F block elements have some fascinating
Yeah.
and controversial applications.
They do. But what's important to remember is that these blocks, they give us valuable information
Absolutely.
about the elements and their behavior.
Yeah.
It's all connected.
It is.
Yeah, this is making me see the periodic table in a whole new way.
That's good.
It's not just a chart, it's a map. It guides us through the elements
That's a great way to look at it.
and their relationships.
Mhm.
But there's more to it than that, right?
You're right.
The periodic table, it helps us predict trends.
Trends and element properties, yes. That's where things get really interesting.
Absolutely.
And that's what we'll dive into next. It's not just a chart, you
Right.
know. It's like a dynamic tool
Okay.
that helps us understand how properties change as you move across
Oh, okay.
or down the table.
Got it, yeah. It's like having a cheat sheet for chemistry.
Yeah.
You were talking about trends and properties
Right.
before the break. Can you give me an example of what you mean?
Sure. Let's look at atomic radius, the size of an atom.
Okay, yeah.
Now, as you move across a period,
Okay.
left to right,
Uh-huh.
the atomic radius, it generally decreases.
Decreases, okay. But wouldn't you think they would get bigger, as you add electrons?
Right. It seems counterintuitive.
Yeah.
It has to do with the pull of the nucleus on those electrons.
Okay.
You see, as you move across a period,
Yeah.
the number of protons in the nucleus, it increases.
Okay.
And those protons, they're positively charged, right?
Right.
So they attract the electrons, which are negatively charged.
Oh, okay. So it's like this tug of war
Exactly.
between the nucleus and the electrons.
Yeah,
And the nucleus gets stronger pull as you go across.
that's it. And the added electrons, they go into the same energy level.
Oh, I see.
They're not really good at shielding each other from that nuclear charge.
So the atom gets pulled in tighter,
Yes.
shrinks.
It shrinks in size, that's right.
Interesting. Okay. What happens as you go down a group, top to bottom?
As you go down, the atomic radii generally increase.
Okay, so it gets bigger going down.
Yeah, because you're adding electrons to new energy levels.
Okay.
Farther away from the nucleus.
Okay.
And those inner electrons, they act like a shield,
They do.
reducing that effective nuclear charge.
The outermost electrons are feeling.
Yeah, so the more electron shells an atom has,
Right.
the larger it is.
Okay.
Because those outer electrons, they're further away.
Makes sense, yeah.
Mm.
It's all about that balance, isn't it?
It is.
The forces.
And this trend, it has real implications.
Oh, really? How so?
Smaller atoms, for example, they tend to be harder
Okay.
and have higher melting points.
Okay.
Because their atoms are packed in tighter.
I see. Okay, so what other trends are there?
Another big one is ionization enthalpy,
Okay.
the energy needed to remove an electron from an atom.
Okay.
And generally, this increases as you move across a period.
So those smaller atoms
Yeah.
with a strong nuclear pull are
Mhm.
holding on more tightly
Yes, exactly. It takes more energy to remove an electron.
to pull it away.
Yeah. And then going down a group,
Huh.
ionization enthalpy decreases.
Because those outermost electrons are farther away.
That's right. And ionization enthalpy is related to reactivity, you see.
Okay.
Elements with low ionization energies, they're more reactive
Okay.
because they can lose those electrons easier.
To form positive ions.
You got it. The alkali metals, for instance.
Yeah.
Group 1, super reactive.
Yeah, we were just talking about those.
Right. They have very low ionization energies,
Okay.
almost begging to lose that valence electron.
They are?
This trend also explains why noble gases are so unreactive.
Right.
They have very high ionization energies.
Okay.
They're stable.
Their electron configuration
Right.
is just so stable.
It is.
I'm starting to see how it all fits together. What about gaining an electron?
Good question. That's called electron gain enthalpy.
Electron gain enthalpy.
The energy change when an atom gains an electron.
Okay, interesting.
It follows a similar trend to ionization enthalpy,
Does it?
but in reverse.
Okay.
So it becomes more negative across a period.
Meaning more likely to gain an electron.
Yes. They want to achieve that stable noble gas configuration.
Oh, right, yeah.
And going down a group,
Okay, yeah.
it becomes less negative.
Because the atoms are larger,
Yes,
that attraction for another electron isn't as strong.
exactly.
Got it. Okay, so we've got size, losing electrons, gaining electrons.
Right.
What other properties can we predict?
Well, electronegativity is a big one.
Okay, what's that?
It's a measure of an atom's tendency to attract electrons in a bond.
Okay.
And it increases across a period, decreases down a group.
So similar to ionization enthalpy.
Yeah. So elements on the right side of the table,
Okay.
like oxygen and fluorine,
Uh-huh.
they're electron magnets.
They are?
They pull those electrons toward them in a bond
Okay, so this property is essential to understanding how they bond together.
to form molecules.
The periodic table helps us predict how they'll interact with each other.
Absolutely. It gives us clues about the types of bonds,
Okay.
whether they'll be ionic,
Ionic, yeah.
where electrons are transferred, or covalent,
Covalent, okay.
where electrons are shared.
Oh, cool. This is really showing me how everything in chemistry is connected. You mentioned there are exceptions to these trends.
You're right. Like any good map, you know?
Yeah.
The periodic table has some detours,
Okay.
some surprises.
I like a good mystery. Tell me about these exceptions.
Okay, so sometimes you get elements
Yeah.
that are diagonally next to each other on the table.
Okay, diagonally.
They show similar properties,
Oh, interesting.
even though they're in different groups.
So they're breaking the rules.
Kind of, yeah. We call that a diagonal relationship.
A diagonal relationship. Okay, give me an example.
Lithium
Okay.
in group 1
Yeah.
and magnesium in group 2.
Okay, so group 1 and group 2?
Yeah. They have some unexpected similarities,
Oh, wow.
like their electronegativities.
Okay.
And they tend to form compounds with similar properties.
So even though lithium is an alkali metal
Yeah.
and magnesium is an alkali earth metal,
Mm-hmm.
they act more like each other.
That's right. Because of their size and charge.
That's cool.
It's not just a coincidence.
Okay.
It helps us to understand them better.
Right. Okay, any other exceptions?
Another interesting one is the inert pair effect,
Okay.
seen in heavier elements.
Heavier element.
Yeah, in the p-lock.
P-block, okay. What happens?
Well, the s electrons in the outermost shell,
Yeah.
they become less involved in bonding.
Oh, really?
Yeah. The p electrons, they do most of the work.
So those electrons are just, like, on strike.
Kind of, yeah. It's due to the size of the atom
Okay.
and other factors.
That make those electrons less available for bonding.
Right.
Okay. Does this have any noticeable consequences?
It does. It can influence their oxidation states.
Your oxidation state.
Yeah, the charges they can have in compounds.
Okay.
For instance, tin in group 14.
Tin group 14, okay.
It can have a +2 and +4 oxidation state.
Interesting.
In the +2 state, it's just the p electrons bonding.
Oh, okay.
And in the +4 state, both s and p electrons participate.
Wow. So a subtle effect
Yeah,
has a big impact.
it does. Highlights the complexity of the periodic table.
I'm sensing a theme here.
Oh, yeah.
Those heavier elements have more surprises.
They do. One of the most dramatic is the lanthanide contraction.
Lanthanide contraction, all right. Tell me about it.
So it's this decrease in atomic radii
Okay.
that happens as you move across the lanthanide series.
Lanthanide series.
Those 14 elements.
Yeah.
In the F block.
The F block, right, tucked away down there. But wait, shouldn't atomic radii increase as you move across?
You would think so, yeah?
Because you're adding electrons.
Right.
But, okay, the lanthanides are special.
They are. You see, as you go across,
Yeah.
The 4f electrons are added to an inner shell,
Okay.
and they're not very good at shielding
I'm not.
from the increasing nuclear charge.
I see.
So those 4f electrons are slacking off.
They are.
The nucleus pulls those outer electrons tighter, and the atom shrinks.
Wow, so even though they're down there,
Yeah,
they still influence the rest of the table.
they do. This contraction has a ripple effect.
Okay.
It affects the transition metals that come after them.
Oh, interesting.
For example, the transition metals in the 6th period.
Okay.
They have very similar atomic radii
Oh, wow.
to those in the 5th period,
Okay.
which leads to similarities in their behavior.
So the lanthanides are causing a bit of an identity crisis.
Kind of, yeah. It's a fascinating example of how it's all connected.
Yeah. This makes me realize the periodic table is more than just a chart.
It is.
It's a story,
Yeah.
a map, a puzzle,
Yeah.
and a masterpiece.
Well said. Well said.
All in one.
It's a testament to science, wouldn't you say?
Absolutely.
Observation and creativity.
Yeah, it is amazing how those subtle effects have such, consequences. I'm really starting to see this
Yeah.
intricate web of connections
Yeah.
and patterns.
Yeah. That's exactly it. That's what makes it so powerful.
Right.
Helps us understand not just the elements themselves,
Yeah.
but how they behave with each other.
Right. So if we know where an element sits on the table, we can, kind of guess how it might react, right?
Exactly. Like, take the alkali metals, group 1.
Oh, yeah.
We know they're highly reactive.
Super react.
Always ready to lose that electron.
Right.
To get that stable configuration.
Like the noble gases,
Right. They're like the, what's the word?
the social butterflies.
Yes! The social butterflies of the periodic table, always looking to bond.
Exactly.
And then you have on the other end, the halogens.
The halogens, yeah.
Group 17, just 1 electron shy.
Yeah, they're reactive too, but in the opposite way.
The opposite way, yeah.
They want to gain an electron.
Exactly. So you could say they're the electron thieves.
They are. They're stealing them.
And because of this, we can predict,
Yeah.
alkali metals and halogens,
Mhm.
they'll react.
And pretty intensely.
Pretty intensely, yeah.
Like a chemical explosion.
Sometimes, literally.
Whoa.
Sodium, an alkali metal,
Yeah.
meets chlorine, a halogen,
Okay.
can be pretty dramatic.
You can?
Sodium gives up its electron
Okay.
to chlorine, boom,
Yeah.
forms sodium chloride.
Wait, sodium chloride, that's just table salt.
It is.
Oh, wow.
Even something like table salt.
Yeah.
It all goes back to these principles.
That's amazing. So we see this in everyday life,
We do.
not just in these, fancy reactions.
Absolutely. These principles extend to, well, everything. All sorts of compounds.
Okay.
Simple molecules,
Yeah.
complex biomolecules
Right.
that make up life. It's
Yeah.
really the foundation for understanding
That whole chemical world.
the diversity of it. Yeah.
Okay, I have a question.
Mm.
We've talked about the main group elements.
Yeah.
What about the less common ones?
Oh, you mean the intertransition metals?
Yeah, those F block elements.
The lanthanides and actinides, they might be less known,
Yeah.
but they have some important uses.
I do.
Lanthanides,
Yeah.
they're used in high-intensity lighting,
Really?
lasers, even the magnets in headphones.
Oh, wow. I never knew that.
Yeah, they're hiding in plain sight.
They are. What about the actinides?
Well, they're known for their radioactivity,
Right.
which can be good or bad.
Right, like a double-edged sword.
Yeah. Uranium, for instance.
Okay.
It fuels nuclear power plants.
Clean energy.
Right. But,
But it can also be used for,
Yeah.
not so good things.
Yeah.
It highlights, responsibility,
Yeah.
ethical considerations.
Definitely. Definitely. Sobering, but important. But, hey, those lighter elements,
Yeah.
they're the real workhorses, right?
Oh, absolutely.
Carbon, oxygen,
The essentials.
they are...
Carbon, the backbone of organic molecules.
Right.
Oxygen, respiration.
Yeah. It's all about life. It is. Their properties, right where they are on the table, they're perfect for life's processes.
Wow, so it's not just about exotic elements.
Nope.
It's about us.
It's about the world around us.
Yeah.
The elements that make it all up.
This has been an incredible journey
It has.
through the periodic table. I mean, it's so much more than just a chart.
It is. It's a testament to human curiosity,
Absolutely.
our drive to understand.
Yeah.
And it's always evolving
Right.
as we find new elements,
Uh-huh.
learn more about the atom.
It will keep guiding us.
It will.
Yeah. Well, I think we've reached the end of our deep dives.
I think so too.
Thanks for joining us on this exploration.
Yeah.
I hope you're leaving with a new appreciation for,
For this amazing tool.
It is.
It's been a pleasure.
Thanks for being here.
Of course, of course.
Keep exploring, everyone. Keep questioning.
Yes.
And let the periodic table be your guide
Your compass.
to the world of chemistry.